All right, today we are on a serious mathematical quest. We're hunting for a single, very special number, a number that sits at the absolute edge of what a simple computer is capable of. And for, 40 years, many thought this number was just impossible to pin down, impossible to prove. So let's start the hunt. So here's this central question, the big mystery we're trying to solve. What's the absolute longest that a really simple program, one with just 5 rules, can possibly run before it finally stops? I mean, think about that. Out of all the possible 5-rule programs, which one is the champion, the one that runs the longest? Finding that number, that maximum, that's the whole game.
Okay, so here's how we're going to break this down. We'll start with this supposedly impossible function. Then we'll see how they wrangled trillions of machines down to a sane number. We'll look at the decider pipeline they built, meet the 13 super stubborn machines that were left, and of course get to the formally verified result. And finally, we'll talk about what this means for the very edge of what we can know.
All right, first things first, we've got to define what we're even talking about here. What is this game? Because it's a game that leads to a function so wild, it's actually literally impossible to compute.
So, welcome to what's called the Busy Beaver game. It was dreamed up by a mathematician named Tibor Radó way back in 1962. The concept, S of n, is pretty straightforward on the surface. You pick a number of states, let's say 5. Then you look at every single possible 5-state Turing machine that eventually halts. The one that runs for the most steps before it stops, well, that's your Busy Beaver. The number of steps it took, that's S of 5. Radó came up with this whole thing because he wanted a really clean, simple example of something that's uncomputable, a function where you just can't write a single program that will solve it for any n you plug in.
And you know, the insane difficulty of this thing was obvious right from the get-go. I mean, check out this quote. Just 1 year after he invented the problem, Radó himself, the creator, said that finding the answer for just 4 states seemed entirely hopeless. So yeah, that really gives you a sense of why S5, the next one up, was this legendary unsolved problem for decades.
Okay, this is the absolute core of why this problem is so monstrously difficult. It's tied directly to Alan Turing's halting problem. See, you can't just write a clever piece of code to find S of n. Because if you had a magic box that could tell you S of 5, you would have accidentally solved one of the most famously unsolvable problems in computer science. Think about it, right? If you knew S of 5 was, say, 47 million, you could take any 5-state machine, run it for 47,000,001 steps. If it's still chugging along, boom, you've just proven it will run forever. But we know you can't do that in the general case. And if that wasn't enough, some of these tiny little programs are sneaky. Proving whether they halt or not is literally the same problem as solving things like the Goldbach conjecture. It's just wild.
So how on earth do you even start to chip away at an impossible problem? Well, the first step is to face the sheer mind-boggling number of machines you have to deal with.
So here it is, the raw number of possible 5-state, 2-symbol Turing machines. It's almost 17 trillion. Let that sink in. 17 trillion. Trying to check every single one of those isn't just hard, it's not happening. Not with any computer we have or could even imagine. It's completely off the table.
But, and this is a huge but, it turns out you don't have to check all 17 trillion. Not even close. Using a really clever method, the actual number of unique machines that need to be analyzed gets slashed all the way down to this, about 181 million. Now, don't get me wrong, 181 million is still an enormous number, but it's not 17 trillion. It's a number that brings the problem from the realm of the impossible into the realm of the merely monstrously difficult.
So how do they do that? The magic here is a technique called tree normal form, or TNF. The best way to think about it is like you're methodically building out a giant family tree of all possible machines. But TNF is incredibly smart. As it builds, it immediately throws out any duplicates. Machines that do the exact same thing just with the states labeled differently. And even more crucial, it has rules to detect when a certain path of construction is doomed to create a machine that will just run forever. The moment it sees that, it just snips that entire branch of the tree off, which saves it from exploring millions or billions of useless variations. It's a super efficient way to generate only the machines that are actually unique and interesting.
Okay, so we've got our list of 181 million suspects. Now what? The next brilliant step was to build an automated assembly line, or a pipeline, to process them. A factory for proofs, where each station is a different tool called a decider. And here's what that pipeline looked like. Each machine goes into the top and faces a series of tests. And look at that first one, the loops decider.
It's the simplest one, and it alone proved that almost 127 million of the machines would run forever. Just gone. Then the next, more sophisticated deciders whittled the number down even further. By the time you get to the end of the automated process, you can see that more than 99.99% of the machines have been dealt with, all proven to be non-halters. It's an incredible display of automated reasoning.
So what is that first super effective loops decider actually looking for? Well, it's looking for the most common ways machines get stuck, which is by, well, looping. On the left, you see a basic cycler. It just gets into a state where it repeats the exact same configuration over and over and over. Easy enough to spot. But on the right, you've got a translated cycler, which is a bit sneakier. It also repeats a pattern, but the whole pattern shifts down the tape each time, kind of like a glider in Conway's Game of Life. What's so cool here from a computational standpoint is that the algorithm they use to catch these is super elegant. It doesn't even need to remember the whole infinite tape. It just has to watch the sequence of states and the machine's behavior to know it's trapped.
Now, for the really tricky machines that don't have simple repeating patterns, you need to pull out the big guns. This is where a much more advanced and highly academic technique called WFAR comes in. The core idea is just beautiful mathematically. It tries to construct what you can think of as a mathematical trap. It uses something called a weighted automaton, which is like a more powerful version of the state machines you might be familiar with. If it can build a trap that describes an infinite set of non-halting configurations, and it can prove that the machine can never leave that trap once it's in, well, then you've proven it will never, ever halt. It's a really powerful way to reason about infinite behavior.
So the automated factory did its job, and it was incredibly successful. But after all that, a handful of machines were left standing. Just 13. 13 super stubborn, sporadic machines that resisted every single automated test thrown at them. These are the final bosses.
And just look at the kind of beautiful, unexpected complexity you find in these final few. This one is called Skelet #10. And what does it do? It's a counter. Actually, it's two independent counters running at the same time. But they're not counting in binary. No, this little 5-state machine is counting in what's essentially base Fibonacci. It uses a deep mathematical idea called Zeckendorf's theorem, where every number gets a unique representation as a sum of Fibonacci numbers. It's incredible. And the human-written proof had to demonstrate, mathematically, that these two counters would just keep ticking up forever, perfectly in sync, never once going out of step and halting.
And if Skelet #10 was a mini-boss, then this was the final boss of the entire S5 project, Skelet #17. This was the last one, the one that held out the longest. Its behavior is just mind-bendingly complex. It's doing something like manipulating lists on the tape using transformations that are related to gray codes, that special sequence of binary numbers. Proving this thing never stops was a monumental effort. It wasn't just a few pages of math. It required its own entire research paper and thousands upon thousands of lines of formal proof code, just for this one machine. And the other 11 weren't any easier, really. They tended to fall into these little families with cool names like finned machines or shift overflow counters. They were all doing complicated things, like running multiple binary counters that had these really intricate interactions and reset conditions. Every single one required its own unique custom-built proof to show it would never halt. So with that final, monstrous proof for Skelet #17 in the bag, all 13 sporadic machines were solved. The entire list was cleared. The work was done. So, what's the number? And maybe even more importantly, how do we really know that the answer is 100% correct? There you have it, 47,176,870. That is S5, the fifth Busy Beaver number. And what's amazing is that this number confirms a candidate machine, a champion, that was first discovered all the way back in 1989 by Markson and Buntrock. We've known about this specific machine for decades, but only now can we say with absolute certainty that it is in fact the record holder. And this gets back to that question of certainty. What makes this result so rock solid, so definitive, is how it was proven. This wasn't just a matter of running a program and trusting the output. The entire thing, from start to finish, was done inside a formal proof assistant called COC. Now, what does that mean? It means every single logical step, the way they generated the 181 million machines, the code for every single decider, and even the logic behind those massive handwritten proofs for the 13 sporadics, all of it was checked line by a computer for logical consistency. It's an ironclad proof that basically eliminates the risk of human error. It's as close to mathematical truth as we can get.
Okay, so S5 is in the books, but this incredible achievement does more than just give us a big number. It pushes us right up against the very frontier of what we can know through mathematics. So what's next? What's beyond S5?
Well, when people started looking at the next step up, S6, they found something different. Something a lot more dangerous, mathematically speaking. They found machines they call cryptids. And these are not like the others. These are tiny little programs whose behavior seems to be directly tied to some of the deepest, hardest, unsolved problems in all of mathematics. For instance, there's a 6-state machine out there, and proving whether it halts or not seems to be the same as solving a problem that looks a whole lot like the famous Collatz conjecture. We just don't have the mathematical firepower to solve problems like that right now.
And that leaves us with this really profound final thought. In finding the 5th Busy Beaver, we've climbed a massive computational mountain. But as we look towards the 6th, it seems like the problem changes. It's no longer just about clever algorithms and computing power. We're running into machines that are tied to things that might just be unprovable. Have we found the exact point where this fun little game about simple computers stops being a puzzle to be solved and starts being a map to the absolute limits of mathematical knowledge itself? It's a heavy question to end on.